Hi everyone, my name is Emily.
And I'm Megan.
And we are both biomedical engineering majors in the College of Engineering. We are excited to be presenting to you our project on using electric scattering spectroscopy for diagnosis, a minimally invasive method for assessing the health and viability of donated kidneys.
First, we would like to take a moment to acknowledge our other group members, Julia Picardo and Ji-Young Chung, our advisors, Professor Amar and Professor Biggio, and our collaborators at BU Medical Center, Dr. Chitalia and Dr. LaFontanza.
So our project begins with the problem of chronic kidney disease, or CKD, which is defined as the gradual loss of kidney function over time. This disease affects about 1 in 7 adults in the United States alone, and almost always results in required transplants for its victims. One of the methods for assessing the health of kidneys is through measuring the extent of something called interstitial fibrosis and tubular atrophy, or IFTA, which are two common biomarkers present in diseased kidneys. For transplant kidneys, or ex vivo, this is done through a basic physical examination. For inpatient kidneys, or in vivo, this is done through a procedure called a renal biopsy, which I will explain later in more detail. So one of the biggest problems in treating CKD today is that the need for organ transplants is increasing. While a number of patients on the transplant waiting list has been steadily increasing over time, the number of kidneys available for transplant has remained fairly consistent. This is due in part to the inaccurate examination method of these ex vivo organs, which results in many of these viable kidneys being wrongfully discarded. Now, a renal biopsy is a somewhat more accurate method for assessing the health of kidneys. However, this cannot be done in kidneys for transplant because it is a fairly invasive procedure in which the kidney is cored using a very large needle and a sample is removed for analysis. This procedure has many drawbacks, including that it is labor-intensive, can still yield varied results, and causes bleeding and/or pain for its patients. In an ex vivo organ, this procedure would cause extensive tissue damage that would render the organ no longer viable for transplant. So to address this problem, we proposed a fine needle-based device that utilizes electric scattering spectroscopy, or ESS, to assess the health of kidneys. The way our device works is that a small needle, which is much smaller than the one used in renal biopsies, is inserted into the kidney. Within the kidney, a pulse of light is shown that is scattered back in a pattern that reflects the properties of that tissue, which becomes altered by the extent of IFTA. This pattern is received by our device and transmitted to a spectrometer, which measures the properties of this scattered light pattern for us to analyze. This measurement is outputted as a 2D plot of light intensity over the 300 to 900 light wavelength region. To start, we broke down our project into 3 specific aims. 1 was to design and prototype a fine needle tip probe, 2 was to test this probe design on a rat model at the Boston Medical Center, and 3 was to find quantifiable metrics of ESS spectra that correlate to disease progression.
Our lab has previously established the capabilities of elastic scattering spectroscopy as a diagnostic tool. Furthermore, in 2019, they provided proof of concept of elastic scattering spectroscopy for chronic kidney disease in a static mouse model. We hope to build upon their work, improve their probe design, and find results that this technology can be a tool to diagnose different stages of disease progression. So regarding our first aim, this can be broken down into 2 smaller subsections. First, the internal fiber optic components and the user experience. Our fiber optic components have to be compatible with the spectroscopy system provided by our lab. They also must fit within a very small needle, approximately 22 gauge. And finally, the fibers must extend to take measurements and then retract when not in use. The user experience was also equally important to us, as it will be clinicians actually using our device. We are inspired by the clicking mechanism of a ballpoint pen, a traditional renal biopsy gun, and the syringe. So our 2 fibers are the 150 micron, which acts as our bright white light source, and the 100 micron fiber, which acts as the coupling mechanism that returns the information to the spectrometer. Those are both encased within 2 types of tubing, which is then connected to our outer 3D printed probe by a Dremel nut and collet fastening system. This was a huge advantage over the previous design because it allows us to actually take out the internal mechanisms and repolish them if needed during the experiment. Our end result is this final probe design that can be operated with only one hand. The user would squeeze that top bar to extend the fibers about 1 millimeter beyond the tip of the needle, and then you can press the side buttons to retract when not in use.
Our next step was to test our device on actual rat kidneys at the Boston Medical Center. Our experiment involved 2 groups of rats. one control group of healthy adult rats, and another group that was administered an adenine-based diet in order to induce kidney disease in them. Over the course of 4 weeks, we used our probe to take measurements from 3 animals per group per week at various sites and depths in order to get as many data sets as possible. The rats' kidneys will also be sampled using the traditional renal biopsy procedure and analyzed by expert pathologists in order to obtain reliable data on disease progression. Due to some delays in collecting data, we were unable to get those results at this time. However, we hope to eventually be able to compare our data to this standard to determine how accurate our device really is. Lastly, to analyze our data, we used Excel to clean our data by removing any poor measurements and then plotted this resulting data sets. These graphs were compared to show the overall trends and extent of IFTA in the kidneys over time. Our overall goal is to identify which trends in the spectrographs best correlate with CKD progression.
And this is our end result. After about 650 nanometers, the data did become fairly noisy, which was expected. So our region of interest is actually from about 300 to about 450 nanometers, because that's what correlates to the most changes in the disease spectra. So between week 1 and week 2, we saw minimal changes as compared to the controls, but by week 3 and 4, there were profound changes in the spectra that we then analyzed different features to correspond to actually how diseased the kidneys were. So as I mentioned, we looked for different features of the spectra that correlate to disease progression, and one that we found that worked very well was the slope between 310 and 370 nanometers. As you can see, the adenine group varied significantly from the control as the experimental run went on, and we saw an increasingly positive trend throughout our experiment. As Emily mentioned previously, we were unfortunately unable to compare our results to the actual IFTA score, which is a score out of 100 on the extent of the interstitial fibrosis and tubular atrophy. That corresponds to a predictive CKD stage if it were in humans, and of course there are also different clinical impacts of that score. Luckily, though, we did have data from a previous 2020 rat model experiment that we were able to compare our spectra to, just so we could get an idea of the actual IFTA score. So for the control weeks, we expect that to have a predictive score of about 0, as there was no external mechanisms that would allow a rat to develop chronic kidney disease. By week 2, there should be about 5% IFTA, and by week 4, the disease is particularly advanced with about 70 to 80% fibrosed. As you can see, this is not at all a linear progression, which does correspond to our results quite nicely.
To confirm that the observed changes in the light spectra among our experimental groups was not due to the natural aging process of these rats over the course of 4 weeks, we performed a single-factor ANOVA statistical significance test on the slope biomarker from the first 3 weeks of the control group. The output of this told us that we obtained a p-value that was much greater than 0.05 and an f-value less than the f-critical value, which allows us to conclude that there is no significant difference caused between the control group means and therefore minimal effects of aging on our data.
So in conclusion, we have designed, tested, and have analyzed the results from a non-invasive device that provided minimal damage to the kidney tissue. We hope that our device will provide more rapid and quantitative sampling and therefore less error and variability for the patients. And finally, this proof of concept can be applied to other applications such as in vivo procedures, thus replacing the traditional renal biopsy gun. And that wraps up our presentation. Thank you so much for listening, and I'm happy to take any questions. Covered everything.
I'll start with a question. Are we on? Yeah. So I'm wondering actually about the last thing that you said in terms of future applications. Can you think about this in terms of what you've talked about as user experience being the person who's administering the test? I'm wondering about user experience as the patient, or in terms of the ways in which you think about how this is going to expand the possibility, right? What your vision is for how much this can do in terms of kidneys in particular and other organs, for how this will result in real differences in what patients can expect.
Yeah, so we hope that this can eventually replace the traditional renal biopsy, which that's done using a ultrasound to identify the location of the kidney because it's very deep in the back. So potentially, since fibers are incredibly flexible, this could be done during a less invasive procedure where the fibers would be inserted in kind of a more discrete location and then fed to the kidney, and then it would just be a matter of a few centimeters or meters in, and you're not actually removing tissue. You're just doing an optical biopsy instead. Yeah.
Thank you.
Thank you so much. Could you explain the correspondence in typical human kidney disease to the weeks that you were showing in the rat model?
Yeah. So this adenine rat model is not linear in its disease progression, but what it is very similar to in humans is that interstitial fibrosis and tubular atrophy forms in different patches. So the tissue is heterogeneous, meaning that you need multiple measurements of different spots in order to get a picture of what is really happening with the full organ. So with a traditional renal biopsy, you're just getting a cord sample of the tissue, and that tissue might not be indicative of the entire organ. So going back to your question, in this adenine rat model, the first 3 weeks are if it were in humans, it would be very, very mild conditions. But by week 4, the disease has progressed very rapidly. In the rats, they were not doing too well by that point. So I was glad it was only 4 weeks. But yeah, so between stage 0 to about 3, you're just, in a clinical sense, patients are really just trying to maintain whatever stage they're in, just by monitoring other conditions such as diabetes or high blood pressure. However, by stage 4 or 5, then you're kind of starting to think about dialysis and eventual transplants, which is when it gets much more serious. But a renal biopsy is the best indicator of what's actually going on in the kidney at any given time. So what the clinicians actually indicated was that if they could do a renal biopsy at any stage on any patient, if it were so easy, they absolutely would, because it's the best way to treat and get the most information from the tissue.